Today's video is the next step in the diagonalization process. So we're going to look at the characteristic polynomial. So I wanted you to recall a couple things. Suppose A is, when I write this notation and I just put a single n, it means that A is an m by n or an n by n square matrix. So when you do that and you only see one n, that's what that means. So lambda is an eigenvalue of A if A times x equals lambda of x for some non-zero vector x. So, and remember what we typically did is we subtracted the other side over, and then we factor out the x. And now, even for there to be non-zero x's available, for this to have a solution, we need that the null space of A minus lambda I is not just the zero vector. So with that in mind, so we need the determinant of A minus lambda I to not equal zero, because we don't want it to be we don't want it to be invertible is exactly what we're looking for. So I'll show you how we apply this. Determine the eigenvalues of, and the matrix that we have, starting off small and simple, 5, negative 3, negative 4, 3. And so what we try to do is, I think I made a mistake up here before I continue. We actually, we want there to be non-zero x's that are solutions. So actually, I want the determinant to be 0. My bad. So what we do then is we look at this matrix, 5, negative 3, negative 4, 3, and we subtract off lambda times I, and that works out to be 5 minus lambda, negative 3, negative 4, 3. So then we do the determinant of that item, and down here is the 3 minus lambda. So we want that determinant to equal 0. And if you recall, the determinant of a 2 by 2, we take the main diagonal, so 5 minus lambda times 3 minus lambda, and then we subtract the other diagonal, minus 12, and that's equal to 0. To solve this then, I'll multiply out and combine like terms as normal. So I'll get 15 minus 8 lambda plus lambda squared minus 12. When I clean up a little bit, lambda squared minus 8 lambda plus 3 is equal to 0. I don't know how to factor this, so immediately I'm going to go to the quadratic formula. So I've written it all out in case you have forgotten this beautiful little formula. Inside of the square root, I got 64 minus 12, so that's 52. 52 is 4 times 13, so I get 8 plus and minus 2 radical 13 all over 2. And then when I simplify, my values of lambda will be 4 plus and minus radical 13. Let me, I guess, throw in a couple of definitions here. I don't know if we're going to call them. P of lambda, which equals lambda squared minus 8 lambda plus 3, is called the characteristic polynomial. And then when I had lambda squared minus 8 lambda plus 3 equals 0, that was called the characteristic equation. Let me do another example. This time we want to compute the eigenvalues. Of the matrix 7, -2, 2, 3. So for these, I'm just going to cut right to the chase and start doing the determinant. So I have 7 minus lambda, -2, 2, 3 minus lambda. And according to the formula, that's 7 minus lambda times 3 minus lambda plus 4. And remember, I'm setting that equal to 0. So I have my characteristic polynomial and equation all in one. Let me go ahead and multiply this out by the FOIL method. I get 21 minus 10 lambda plus lambda squared plus 4. And that's equal to 0. Otherwise, we get lambda squared minus 10 lambda plus 25 equals 0. This actually factors into lambda minus 5 squared. That equals 0. So when I write my eigenvalues, I'll write 5 and 5. This we write to indicate that its multiplicity is 2. So realistically, we'll work on solving various polynomials and setting them equal to 0 later. Right now, let's concentrate on finding just the characteristic polynomial, because even if we don't have a lot of work towards it, you can still graph these things and find out the zeros that way. But let's do a more complicated one. Compute the characteristic polynomial of, this time I'm going to do a 3 by 3. I have 0, 3, 1, 3, 0, 2, 1, 2, 0. So let me cut right down to the chase. Remember, P of lambda is the determinant of A minus lambda. So 0 minus lambda, 3, 1, 3, 0 minus lambda, 2, 1, 2, 0 minus lambda. Of course, 0 minus lambda doesn't do much. It's just negative lambda for each of those pieces. So I have negative lambda, 3, 1, 3, negative lambda, 2, 1, 2, negative lambda. And I'm ready for my cofactor expansion. So So I'm going to expand along the first column. Start with negative lambda. So for the negative lambda, cut out the row and the column, and we're left with negative lambda, 2, negative lambda. Now don't forget to alternate the signs as you go down the column. So for the 3, I'm going to get rid of this row, and I'm going to get rid of this column, and I'll be left with 3, 1, 2, negative lambda. 3, 1, 2, negative lambda. And then finally plus the 1. And for this, let me cut out the row and the column, and I get 3, 1, negative lambda, 2. So let me go ahead and make all these computations. Remember, this is P of lambda, the characteristic polynomial. For the first piece, I'll get lambda squared minus 4. The second one, I'll get negative 3 lambda minus 2. And for the third one, I'll get 6 plus lambda. Now I notice the highest power that occurs of lambda in here will ultimately be lambda to the third. So let me go ahead and collect all of my lambda to the thirds and then work from there. I see I got a negative lambda to the third, but as I look through the entire polynomial, I have no other lambdas that are that high of power. So I'll have negative lambda to the third. Now I'll go looking for lambda squares. So do I see any lambda to the second power? Well, there's one, but unfortunately we multiplied by that lambda to make a cube. And as I look, no lambda squared there, no lambda squared anywhere. So I'll go ahead and move on to just plain old lambda. And for that, I will start with positive 4 lambda. And I said to alternate signs, but I did not. My oh my. And then for this one, I'll get plus 9 lambda. So I have 4 plus 9 is 13 lambda, plus 1 more lambda is plus 14 lambda. And then finally the number part, I'll get 6 plus 6 is 12. And next section and whatnot, we'll work on ways of breaking these down and setting these equal to 0 and kind of reviewing some of your polynomial rules that you may or may not have forgotten. For my next example, let's compute the characteristic polynomial and this time we have another 3 by 3. It goes 5, negative 2, 3, 0, 1, 0, and 6, 7, negative 2. And so for my solution, I have P of lambda is equal to the determinant of, and I have 5 minus lambda, 0, 6, that's down the first column, negative 2, 1 minus lambda, 7, 3, 0, negative 2 minus lambda. And I'll do like I did before, I'll do cofactor expansion, but this time I see a very nice opportunity to save myself a lot of work. And that's if I go along the second row, I only have one non-zero thing to do. If we need to know what the sign is, whether it's positive or negative, notice that 5 minus lambda would have been a positive sign, and this would have been a negative sign. Then when I go down, this would have been a positive sign. In fact, always on the diagonal, the signs are always positive with these. So I get 1 minus lambda times the determinant of the submatrix. Get rid of the row and the column that it's in, and you'll essentially you will pick off just the items in the corners. And let me go ahead and multiply it out. So I get 1 minus lambda times, and so the first thing will be here, 5 minus lambda times negative 2 minus lambda, and then minus 18. And I'm just going to work inside of there to simplify as much as possible. Remember, you ultimately be setting these equal to 0 and solving. So I'll keep that in mind. I'll see if this can factor, I will factor it if I see an easy way to do it. Let's see, we have negative 5 lambda plus 2 lambda is negative 3 lambda plus lambda squared minus the 18. And that's technically done, but suppose I was asked to solve it and set it equal to 0, I'd probably do some of this stuff. I'll get lambda squared minus 3 lambda minus 28. And that does factor, because 28 is 7 times 4. And I know that you can get a negative 3 by doing 4 minus 7. So we have P of lambda equals 1 minus lambda times lambda, guessing minus 7, times lambda plus 4. Let's check those out. Lambda squared plus 4 lambda minus 3 lambda minus 28. Next, let's compute the eigenvalues of, this time I'm going to have a 4 by 4 matrix. I have 5, 8, 0, 1 down the first column, 0, negative 4, 7, negative 5, 0, 0, 1, 2, and finally 0, 0, 0, 1. Notice it's a diagonal matrix. And you can find the eigenvalues of a diagonal matrix just by looking down the diagonal. It's something that we proved in the last video. But let me just show you for absolute certain how you can get them, how it does relate to just the items on the diagonal. So when I go to do my characteristic polynomial, I'll subtract lambda from each of the diagonal terms. Now, one thing I know that you do know is that the determinant of a diagonal matrix, or what your book calls a triangular matrix, is you just take the product of the items on the main diagonal. So I have 5 minus lambda times negative 4 minus lambda times 1 minus lambda times 1 minus lambda. And there's your characteristic polynomial for this matrix. Very simple with diagonal matrices. This one here is what they call a lower diagonal matrix. So as a quick example, compute the eigenvalues of that last matrix. So basically, you would set 5 minus lambda times negative 4 minus lambda times 1 minus lambda times 1 minus lambda, all equal to 0. And we would get lambda equals 5, negative 4, 1, and 1. So you can see that we have two of our eigenvalues are of multiplicity 1, and the eigenvalue lambda equals 1 is of multiplicity 2. The multiplicity will come in handy later. Right now, we're just laying the, what they call it, the foundation for the work that we're going to do next. Theorem. Let A be an n by n square matrix. So that A is invertible if and only if 0 is not an eigenvalue. Now we know that 0 can be an eigenvalue, but the eigenvectors that are created cannot be the 0 vector. So let's take a look and see what happens here. We know that A is invertible. That's the same thing. That means it's a little if and only if, double arrow implication. The determinant of A does not equal 0, which is the same as the determinant of A minus 0. That 0 inside of there is the 0 matrix, but it doesn't change anything. And I can do this business. Determinant of A minus 0I. Now, it's the same thing. All I've done now is change this 0 matrix for the matrix I times the scalar 0. The reason why I'm using the scalar 0 is because that's acting like my lambda. And so this is if and only if 0 is not an eigenvalue. So that was pretty easy. I got a couple of theorems in a row that I want to do. Theorem. Here we have, I think this may have been proven before, but I'm not really sure, so I'm going to do it again. The determinant of A is the same as the determinant of A transpose. So what I think we should do probably is let me set up my A. Remember, it'd be like A11 all the way down till AN1, A1N, ANN. All right, so let me expand. Let's expand along the first column. Since I can choose whatever I want, column or row, whatever column or row that I want. Determinant of A, so I'll start going down this column here. I'll have A11. Do you remember then it was times C11, the cofactor? That included the positive or negative sign was inside of that. Then we had A, as I'm going down, the first item is changing, the first index of the 2 index part. So it's 2, 1, then A31 all the way down to AN1. So we have 2, 1 times C21 plus dot, 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 plus AN1 times CN1. Now, if you're wondering why I'm not alternating my signs, I mentioned it a second ago. The sign is inside of the cofactor. So this is the formula that I get. I think it may be easier to see it this way as a sum. I equals 1 to n. We have AI1 times CI1. So there's the determinant of that matrix. Now, A transpose will look like the following. I'll still have A11, but this time, what was the first row is now the first column, A1n. And then along the first row, instead of having A12 next, you'll have A21, and then you'll have AN1. So the first column became the first row. And then it still goes to the same spot, ANN, when all is said and done. But all I care about really is the first row, because now I'm going to expand about the first row. So the determinant of A transpose, well then I'm going to have A11 times C11, but then I'm going to have A21 times C21 plus plus AN1 times CN1. And if you look, simply by going across the first column of the regular matrix, look at what I get for the determinant, and if you look at what I get for the determinant here, it's the same. So that takes care of that theorem. And if you want, you can say the determinant A transpose will be the same thing. I equals 1 to n, A I1 C I1. Theorem: A and A transpose have the same characteristic polynomial. And this one here is not that hard to prove either. We look at P of lambda, we know is going to be the determinant of A minus lambda I. But now the determinant of any matrix is the same as the determinant of the determinant of the transpose of it. So here's my matrix. A minus lambda I is a matrix, and I'm taking its transpose. One of the properties of transpose is that you can distribute it inside. Now, the only difference here is that the transpose of I is still I. So you can see this here then, this is the characteristic polynomial of A transpose. So, and this was the characteristic polynomial of A. So we get the same thing for both of them. Now this next thing may seem out of left field, but it's going to be very important for the next thing that we do. This is the notion of similar matrices. So we're going to let A and B be square n by n matrices. A is similar to B, so similar is the word I'm talking about, if there exists a matrix P in M sub n such that A equals P B P inverse. Obviously, the P that is involved should be invertible. So I think I say that in this part right here. And so that's what you're looking for. That's called similarity. Like I said, it seems like it's out of left field, but this is exactly the kind of thing that we're going to be working on next time. You'll see, well, you'll have to wait. But you can sort of get an idea of what's going on with this next theorem. If A and B are n by n square matrices and are similar, then they have the same characteristic polynomial. prove that, let's start with the following. We have A equals P, B, P inverse. So suppose we have such a matrix P where this happens. All right, so we'll start with P of lambda, the characteristic polynomial for A, will equal the determinant of A minus lambda I. And I'll go ahead and substitute the PBP inverse for A. And then at this point, there's a little trick that I can do. I can write I as P times P inverse. But what this allows me to do is to factor out a P on the left and a P inverse on the right. So let me kind of do it this way. And then what I can do, one of the properties of determinants that has long ago been proven is I can break this up in determinant of P times the determinant of B minus lambda I times the determinant of P inverse. Now I don't know if you remember this or not, but I can move these around. Multiplication is commutative for the determinant. Well, multiplication in the set of real numbers is commutative. And then I'll go ahead and combine the two determinants on the left here, determinant of P inverse times the determinant of B minus lambda I. PP inverse is just I, so that's the determinant of I times the determinant of B minus lambda I. Of course, the determinant of I is just equal to 1. I'm being very specific. I'm writing all the details just in case you have to look at this later on and need some help. And of course, all of this is just the determinant of B minus lambda I.